Hello everyone, Assalamu alaikum. Welcome back for another video in the series of VLSI systems. In this video, we are going to discuss about the basic examples of CMOS gates. We have already discussed in the previous video about basic CMOS circuits, that is inverter, CMOS based NAND gate and CMOS based NOR gate. Now in this video, what we are going to discuss is about how to make CMOS based exclusive OR gate, exclusive NOR gate. Then we will discuss how to make a complex gate out of CMOS circuits. And the last thing that we are going to discuss is to make a CMOS based full adder circuit. So first of all, let's discuss how to make CMOS exclusive OR gate. For that, we need the logic equation for CMOS exclusive OR gate. Now, we know that the output Y is equal to A B bar plus B A bar. And if you recall, a CMOS based gate generates an inverted output. So when we implement our logic equation, what we need is the inverted output. As you can see that this is not the inverted output, so we generate the inverted output by taking double bar of this. So inverted output for this case turns out to be A dot B plus A bar dot B bar. Now let's look at the truth table of an exclusive OR gate. It generates an output of 0 when both of its inputs are same, and it generates an output 1 when both of its inputs are different. Now let's try to build this circuit. As we have generated an inverted output which consists of AB plus A bar B bar, as our output contains two product terms and these are added together. So we know for pull down network, if there is a product term, then this product means the transistors are in series. And since there are two product terms in this equation, we have A dot B and A bar dot B bar. So A dot B generates this part and A bar dot B bar generates this part. Now what we need to do is combine these two parts by combining them in parallel, because addition means taking the parallel of these two terms, and these two terms are combined in a parallel way like so. And the pull up network is the complement of pull down network. So as you can see, if we take the complement of this one, this is the equation that is generated: A dot B bar plus B dot A bar. And if we make this circuit, what we get is A dot B bar because they are in series, and B dot A bar and they are in series, and both of these networks are in parallel to each other. And this completes our exclusive OR gate. Now let's quickly test out the functionality of exclusive OR gate, whether we have made the right gate or not. So for the first input, both A and B are 0. Let's check it out. A is 0 and B is 0. So this whole network is off, and this series network is on. And what about above? Because this is 0 and this generates a 1, B prime is 1. So this network and this network all are shut off. Only this network is on. So the output is 0 as predicted. For the next input, A is 0 and B is 1. If we put A 0 and B 1, this network is off, and here again this network is again off. What about the pull-up network? A is 0 and B is 1. So this series network is on, and because this network is on, the output will be VDD, which is 1. Similarly, for A1 and B0, this same scenario happens in the pull-down network. Both the networks are off, and in the pull-up network, if you look at this left-hand side, A is 1, so this network will be turned off. But for this one, A is 1, so its inverted input will be 0. So this PMOS transistor is on and this one is on because it has a logic 0. So the output will be VDD, which is 1. And for the last input, both A and B are 1. So if we consider the pull down network, both A and B are 1. So this one is turned on and all the other input combinations are 0. So the output will be 0 in this case. So our implemented exclusive OR gate is performing as predicted. Let's discuss about the exclusive NOR gate. The output logic equation for exclusive NOR gate is A dot B plus A bar dot B bar. And we know that the output of a CMOS based gate is an inverted output. So we need to invert this equation, and the inverted output for the logic gate turns out to be A dot B bar plus B dot A bar. And this is what we are going to implement in this circuit. Before building the circuit, let's look at the truth table for exclusive NOR gate. An exclusive NOR gate generates a one logic whenever both the inputs are same, and when both the inputs are different, it generates a logic of 0. Now let's build the circuit. As we can see, the inverted output equation gives A dot P bar and B dot A bar. So we have A dot P bar represented here as a series combination, and similarly B dot A bar representing here as a series combination. And because both are being added, so both these terms will be combined in a parallel way. Similarly, for the pull-up network, what we can do is implement the original equation. So for original equation, we have A dot B plus A bar dot B bar. So to implement this, we have A dot B here in the series combination and A bar dot B bar here in the series combination. And both are being added, so we combine both these terms by combining them in parallel way, like so. And hence they produce the output, inverted output. Now let's test the functionality of our gate. For the first test, A and B are 0. This should produce an output of 1. So if we look at the pull down network, if both A and B are 0, then neither this part nor this part is turned on. And if we look at this one, A and B both are 0. So this circuit is turned on and the output will be VDD because VDD will pass through here. For the next example, A is 0 and B is 1. So in the pull down network, this part will not be turned on because A is 0. So this circuit will be turned off. Whereas this part, because A is 0, so A bar will be 1. So and B is 1. So this part will be turned on and the output produced will be the ground, that is 0. So this generates 0. For the next example, A is equal to 1 and B is equal to 0. For the pull down network, this part is turned on as A is equal to 1 and B bar is equal to 1 because B is equal to 0. So the output produced will be ground. And for the last part, A is 1 and B is 1. Neither this part nor this part in the pull down network is turned on, and in the pulled up network, this part will not be turned on, but this part will be turned on because we are giving A is equal to 1 and B is equal to 1, and both are complemented inputs here. So in this case, A will be 0 and B bar will be equal to 0. So this network is turned on and the output produced will be VDD. So this confirms our construction of exclusive OR gate. Next, we will discuss about how to build a complex CMOS gate, which is neither an inverter, NAND gate, NOR gate, exclusive OR gate, or exclusive NOR gate. So in this example, we are going to implement this logic, which is D plus A dot B plus C. Here, let's try to build this function. We have 4 input gate. So we have inputs A, B, C, and D. Let's start with the parentheses. We have B plus C, and because they are adding up, so we know that if we are adding, that means we are implementing the transistors in parallel fashion. This is represented here. And the parallel combination of B and C is ANDed with A. That means A will be in series with the combination of B and C. And again, D is being added with this term, and this term is represented here. So we combine D with this term in parallel. And for the pull-up network, it is the complement of pull-down network. So as you can see, B and C are parallel here. So B and C will be in series here in the pull-up network. And the combination of B and C is in series with A here. So in the pull-up network, it will be in parallel here. And the combination of this whole term and D is in parallel. So in the pull-up network, it should be in series. So this concludes our construction of a complex CMOS gate. Now, the last example that I'm going to discuss is how to make a full adder using a CMOS gate. We know that full adder is a combination of two logic equations, a carry term and a sum term. Let's first implement the carry term and then we will move on to the sum term. So this is the basic equation for a carry term, A dot B plus C dot A plus B. And this is the complemented output. So remember that this circuit will produce a complemented output. The C here represents the carry in term and A and B represent 1 bit input that we are going to add. So let's implement this function. First we will implement the pull down network. For pull down network, we have first this A dot B, and this should be represented in the pull down network by combining them in series. So this is A dot B. Then we have A plus B, which is the parallel combination of A and B, and they are being combined with C by adding C transistor in series. So this is the representation of C dot A plus B. This completes our pull down network, and for pull up network, this should be the complement of what is provided in the pull down network. So as you can see, A and B are in series here, so A and B should be in parallel in the pull up network. Similarly, A and B are in parallel here, so A and B should be in series in this network, and they are in series with C, so they should be in parallel with C here. And because both of these networks are in parallel with each other, so they should be in series in the pull-up network. So this is how you can represent a carry term. Another thing that we can reduce from it is if we want to remove redundancy, we can simplify our circuit and make it a symmetrical one. Now, how you can remove the redundancy is by attaching this part of your circuit, A dot B, towards directly VDD and separating this part and C in this way. And the pull down network remains the same. Now you can see that both your pull down network and pull up network are exactly the same. So this is one form of a symmetrical circuit. Let's try to build a sum circuit for full adder. Now we know that the sum is exclusive or of A and B and carry in. So if we expand the terms, we get this equation, which is A dot B dot C plus A dot B bar dot C bar plus A bar dot B bar dot C plus A bar dot B dot C bar. And this whole output is actually inverted. So what we get out of this circuit will be the inverted of the sum. Now, how to implement this one is quite simple. For the pull down network, we have A dot B dot C. So all of these are in series as shown, A dot B dot C. Similarly, for the next one, it is A dot B bar dot C bar. So it is A dot B bar dot C bar represented here. Similarly, for the next part, it is a bar dot p bar dot c, which is represented here, a bar dot p bar dot c. These negative signs are actually not negative, these are actually bars. The last term is a bar dot p dot c bar, which is represented here, a bar dot p dot c bar. And all of these are combined in a parallel way, so we are combining them in parallel like so. You can see that we have reduced our number of transistors in this way. And for the pull-up network, it should be the complement of the pull-down network. So we can draw the pull-up network like so. I hope this video was helpful. If you have any questions, leave them in the comment box below. Don't forget to like, share and subscribe the video, and I'll see you in the next video.